So students, welcome back. We were talking about the different properties of the nucleus, and we again went to speak about the quantum properties of the nucleus, and we saw that the nucleus has got certain quantum numbers which are very similar to the atomic case, where the electron has got quantum numbers. We have the principal quantum number n, the orbital quantum number L, then we have ML, which is the magnetic orbital magnetic quantum number. Then we have the spin quantum number, and correspondingly we have MS, and then the total quantum number J, which is equal to L plus S. Now after these well-known quantum numbers, we went off to talk about the isotopic spin quantum number, which is denoted by capital T. So I did not tell you that it was denoted by capital T. So what is this isotopic quantum number? It was at first it was introduced to show the difference between a proton and a neutron, and for the proton it is plus half. I think I made a mistake in the part A of this class, and I said that T is equal to plus 1. No, it is plus half, and for neutron it is equal to minus half. So this is the isospin. It's also called the T-spin. It has got several names. So later on it was found that all elementary particles taking part in nuclear reactions, they have got a isotopic spin, and we'll talk about it later. Now let us restrict ourselves to only the nucleons inside the nucleus. So this is the isotopic spin quantum number. Then again for T, we have just as we had for L. You remember, for L we had twice L plus 1 values. Similarly for T, we have twice T plus 1 different values, and when I take 2 into half, because half is the value, it's the absolute value, so here T actually is equal to half, and this is called Tz. In a similar way, as if you remember, ML is also known as Mz, where a magnetic field is applied along the z-axis. So Mz, and similarly we have a Tz here, is 2 into half plus 1, which is equal to 2. That means Tz has got two values. So this is not Tz, so different values of Tz is like this. So we know that for multiplicity, it goes from 2 from T to minus T. So it will definitely be half to minus half. We have got only two values. That's why we have under this nucleon, under this category of nucleon, which has got a isotopic spin of T, T can take two values. T is equal to half and T is equal to minus half, because it goes from minus T to plus T. So this gives the two members of the family of nucleons, which is the proton and the neutron. So as I have told you, we'll be discussing about these things later on when we study the elementary particles, which comes in the last unit of your syllabus. For now, it's enough to know that there is a special type of quantum number called the isotopic quantum number. Okay, so done with it. Now we go to something again different, which only comes in quantum systems, that is something called the parity. So what is this parity? So parity actually is a property describing property of the wave function. Actually, it is a property of wave function describing a quantum mechanical system. So students, if I may remind you what is wave function, you know that by wave particle duality, every particle in motion is equivalent to a wave moving, which is called the wave function, which is called the matter wave. So this associated with, just as in case of other waves, mechanical waves, we have something like this xt. Here this matter wave is denoted by psi, and psi is a function of the position, which I can denote as r. R definitely will consist of x, y and z, and also t. So you see this is psi, and this is the wave function. So the property of the wave function describing a quantum mechanics is, there's one particular property that describes a wave function, and that is called the parity. Now if I have got something like this, now for a nuclear system, this psi is also a function of spin in addition to the position coordinates, like this. See, these constitute the position coordinate, and s is the spin coordinate. So this is a wave function describing a quantum mechanical particle like the nucleon and proton. Now what do you mean by students, keeping aside what we are doing, what do you mean by quantum mechanical particle? Quantum mechanical particle has to be so small that its de Broglie wavelength is observable. As you know, lambda is equal to h by p is mv. So if lambda has to be observable or has to make a effect or a difference, then m has to be very small. So obviously this idea of wave particle duality would be applicable only for in the very small world where m is very small, and obviously the nucleus is a very small world where the masses are very small. So that's why we are talking about these quantum mechanical properties. So psi is a function of x, y, z and s. Now let's describe what is parity. Parity is a very much mathematical quantity. It's like this: if psi x, y, z, s is equal to psi minus x minus y minus z s, then we say that the system has got a even or positive parity. But then if psi x, y, z, s is equal to minus of psi minus x minus y minus z s, then we say that the system has got odd or negative parity. So now look at this. This is x, y, z, and this is minus x minus y minus z. Look at the first equation. See, when x is substituted by minus x, y by minus y, and z by minus z, we see that the wave function remains the same, which means that x changing to minus x, y to minus y, and z to minus z is definitely the reflection parity, reflection symmetry, is it not? That means psi remaining same even after the coordinates are being reflected means what? Let's look at this one. If this is x, then this is minus x. That means it's the same here and same here. And what about y? From here and here. So it's called reflection. So symmetry of x is said to be symmetrical about the y-axis and so on. So this property is also called the property of reflection symmetry. So again, we'll again come back to parity later on, just as we'll come back to isospin quantum number. So we learned the second one, the second new property that is associated with a nucleus, with the nucleons, that is parity. Now we move on to the third property, that is the something called the quantum statistics. So what is this? Actually, these statistics form the base of statistical mechanics, which is a very important branch, especially for the small world where we have large number of particles, each of very small size. So when actually statistics applies to a large number of observation, may it be large number of observation or large number of particles, when you deal with them, we require statistics. But then when you are dealing with very small particles, we have quantum statistics. So this is applied to particles which are theoretically indistinguishable. So they are theoretically indistinguishable. Both theoretically and practically. I should have written here practically and practically indistinguishable. So actually it has been actually not found that all particles have been distributed, into two groups as fermions and bosons. Fermions are those particles which obey Fermi-Dirac statistics, and bosons are those which obey the Bose-Einstein statistics. So these are two statistics, and in case of Fermi-Dirac statistics, the particles have got odd parity and they have got a spin which is an half into integer. So it's also called half integral spin, and this is even parity, and this is spin is integral spin. So I'll stop here today, and we'll come back to these three qualities of this quantum properties of the nucleus in our